Okay, this is homework 2. EES, download the starter code. And this is a PDF. This is what the homework looks like. Let's zoom in. A graduated cylinder with diameter DCM is equal to 3 centimeters and has 4 inches of water in it. Our inputs is DCM is equal to 3 centimeters. Let's look here. Down here we have D is equal to DCM, which is 3 centimeters. We convert from centimeters to meters. And has 4 inches of water in it. So the length, well, let's call the height. The length, whatever, is 4 inches. And we took L to be the 4 inches, convert that from inches to meters. Let's read the first question. Determine the velocity of the water leaving the hole. Okay, so for part A, we're given that the velocity of the water leaving the hole is given by this equation. V is equal to 2 square root of G times L. This is equal to 2 times square root of 9.81 times L. L being 4. Let's just write L. This is 4 inches. Here, we need to convert that to meters. And we can just do that really easily in EES. So here, let's write V, which is velocity, so velo, is equal to 2 times square root. And it's going to be G, which is here, which the starter code already gives us, 9.81 meters per second squared. G times L, which is literally L. And let's calculate. Let's see what we have. We have velo is 1.997. So we right click this and put in the units now. Meters per second. Click OK. Look at part 2 or part B. Determine the mass flow rate associated with the water leaving the hole. M dot out, okay? Okay, so M dot out is, actually let's write on our answer, because why not? Velo is 1.997 meters per second. So for part B, we have M dot out. M dot out is going to be equal to, it's a product of the velocity. So velocity is velo times the area of the hole times area times density of the water, rho. So let's see what's given. We can see that rho is given here, so m underscore dot underscore out. So this is what the variable is, and it needs to be equal to this when we calculate. So m dot out is equal to rho, which we have here, times area, which we don't have, velo, which we do have, which is here. Now, what is area, right? So area is equal to, this is area of, let's see, area of the hole. So area of this hole right here, which is d hole cm, right? So normally we would do 0.2. This is in centimeters. We need to convert this to meters. Take this entire thing, square it, divide it by, times pi divided by 4. This will be area of the hole, right? We can just do all that in EES pretty easily. So we can see here that the diameter hole is given, which is 0.2 centimeters, and that d hole is going to take that 0.2 centimeters, convert from centimeters to meters. So we can just do d hole times d hole squared, right? It's pi d squared divided by 4. So we also have pi times d hole divided by 4. So this entire thing here, do divided by 4. And let's do this just so we can see better. This is the area of the hole. So let's calculate, and m dot out is 0.006273. Right click, put in our units, kilograms per second. And we can write down this answer is equal to 0.006273 kilograms per second. Okay, now let's look at part C. Determine the mass flow rate associated with the water entering the cylinder, m dot n. Okay, so m dot n will be equal to, it's the product of the volumetric flow rate and the density. Okay, so volumetric flow rate here is 10 centimeters, 10 cm squared or cubed per minute. This times the density times rho, basically. But we want to convert this entire thing. So that right now it's in centimeters, so we want to convert this centimeters cubed to meters cubed. It's in minutes, we want to convert to seconds. And doing that on paper takes a long time. We can just do it ease really fast. So m dot n is equal to rho times, this is 10 centimeters, that's n dot v dot n. Basically, this is equal to rho times v dot n, because this volume is changing with respect to time. That's why we write v dot n. And we have 10 centimeters cubed divided by minutes. We convert from centimeters cubed divided by minutes to meters cubed divided by seconds. So just v dot n. So m dot n is equal to 0.001667, and that matches. So we can just right click, put in our units, kilogram per second, right OK. This is equal to 0.000167 kilograms per second. Okay, now let's go to part D. Determine the mass, the rate that the mass is being stored in cylinder, dm dt. Okay, so dm dt. Just know that this is the mass changing with respect to time. This is pretty easy if you think about it. It's just the mass that's coming in with respect to time minus the mass that's leaving with respect to time, right? It's just that, so like if we have like a cylinder, right? Something's going in, something's going out. The mass in here is just equal to this minus that. And this is pretty simple. We're given both, so it's just going to be this minus this, right? This value minus this value is equal to, we can just do that. E is pretty simple. This is dm dt is equal to m dot n minus m dot out. And we can click calculate m dot n minus m dot out. Where is it? dm dt is equal to negative. Yep, that's right. So it's equal to negative 0.006106, right? This is kilograms per second. Now let's look at determine the rate at which the level of the water in the cylinder is changing, dl dt. Okay, so this requires a little bit of thinking. So our goal is to find dl dt. If we think about this, right? If we think about this, we know that the mass is equal to density times volume. Volume is equal to area, the cross-sectional area times the length. So density times area times length. If we write dm dt, the rate of the mass, the change of the mass with respect to time, right? This is equal to, density never changes. Density of water, it just stays at 1000, right? Area, cross-sectional area, which is this area right here, right? This, if this is a circle, this doesn't change either. That doesn't make sense, right? So it's area. Length, the length, dl dt, this is changing with respect to time because some is going in and some is leaking out. And we have this value right here showing that it's going out faster than it's coming in because it's negative. And this is kilograms per second, right? So we have a dl dt because the length is changing. And let's just separate variables because we want to find this, so let's isolate this. So we have dl dt is equal to 1 over, we don't even have to write it like that. We can just write dm dt divided by rho over a, right? Divided by rho times the area. And we have this, rho is given, which is 1000, times the area, which is also given, right? So dl dt, centimeters per second squared. Okay, so And if we do everything, it's in meters per second, right? We need to change it to centimeters per second. We'll do that in a second, though. This is equal to, we have dm dt on top, divided by rho, which is 1000, which is just rho, times the area. And the area, we're gonna need the area, the cross-sectional area of this entire cylinder, which is dcm, which is 3 centimeters. dcm is 3 centimeters. Where's that? 3 centimeters. And we have dcm converting from centimeters to meters. Actually, now that we think about it, maybe we can just use dcm instead. So let's do dcm squared, right? Because it's pi r squared, or pi d squared divided by 4 in this case. So let's do pi d squared. Divided by 4. Rho times this is the area. And that should be it. I think. What do we have here? Negative 8 times. Okay, that's not right. Instead of DCM, let's just use D here. Pi squared divided by that. It was convert. That makes more sense. Convert, right? From centimeters, comma to meters. No, from meters to centimeters. Here, there we go. And that should match, and that does match. And we can just right click and write cms per second. Click OK. Everything matches up. And we're done, right? So here's our first set of values, inputs, and it says if we change the inputs to 4 and 0.1, so let's do that. 4 and 0.1. Calculate. We should get these values right here. So velo is 1.997, matches up. M.out is, where's M.out? M.out is 1568, that matches up. M.in, 1667, matches up. DMTT, 1402, that matches up. DLDTCMPS is 11115. Okay, so everything matches up. And all you gotta do is click save, submit it to Canvas, and that's the code right here. Pretty simple.